All right, everyone. Welcome to lecture. If you'll remember, last time we discussed the discrete Fourier transform. We introduced it, we worked through it mathematically. Today, we will extend our discussion. We'll do an example and talk about some of its, the discrete Fourier transform's properties, and that will bring us to the end of class. So first, just to review what we talked about last time, these are the notes that are on Blackboard now. So we have a signal that we could consider in time or in space, some one-dimensional signal, f as a function of x. And we're sampling that signal at locations x0, x1, x2, all the way to xn-1. So that's n samples. We have n samples. And here are our sample locations. So that's f of x0, f of x1, and so on. And what we want using the discrete Fourier transform is to get an array or a vector of frequency components where f0 would represent the low frequency components, or specifically the DC value. And fn-1 would represent the highest frequency possibly detected in your sample vector, your signal vector. Now we said in order to get this capital F signal, this frequency signal, we could do a matrix multiplication. So we multiply our signal vector by what we called the DFT matrix. And last time we showed what the values inside of the DFT matrix would be. As a review, we determined those by using this equation. This is the discrete Fourier transform equation, where this little f represents your signal and the big F again is the frequency component at kth sample. Okay, so we multiply over from j equals 0 to n-1, we multiply fj, so any sample of j, by this value here. Now we redefined e to the negative I to pi to be omega n, excuse me, e to the negative 2 pi over n. We defined that as omega n. So then we were able to rewrite this using that definition to rewrite it like this. Okay, so we have fj times omega n raised to the jk. Those are the only components of the exponent that were left. All right, so we were able, by stepping through j equals 0, 1, 2, all the way to n-1, and k the same, we were able to determine this matrix. So what are we multiplying f0 by? What is this? For any given value of j or k. So if j is there, k is here. For any value of j and k, what is this? So we determined that matrix here. And we called this matrix, again, the DFT matrix. Omega n, by the way, was called the fundamental frequency. All right, so if you recall, because omega n has I, that's the square root of -1, it's complex, which means that the output here is also complex. The magnitude of our frequency signal, fk, is equal to, it's basically representing how much of any frequency component is in, or how much that frequency component is contributing to our signal. The phase of fk represents the phase of that sinusoidal signal, basically how shifted it is in x, if x is space or x is time, whatever it is. All right. So what we're going to do today is one simple example. So let me go back to here. What we want to determine is, let's suppose that f equals 1, 2, 3, 4. Now, this is also in your notes in that same file, but we're going to work through it together. So f is 1, 2, 3, and 4. What is f? So let's determine the DFT of f. Let's go back to the screen. I'm going to determine the DFT of F. So again, we have F. Actually, let me add a new page with dots. Okay, so we have F is equal to 1, 2, 3, 4. What is capital F? If you remember from the matrix, you'll know that capital F is also going to have 4 components. It'll be the same size as lowercase f. Okay, it's 4 components here, 4 components there. So what do? Well, we could go back and look at our equation. Basically, we need to determine the DFT matrix. Okay, so we need to determine the DFT matrix. But in order to determine the DFT matrix, first, we need to determine what omega n is, because the DFT matrix is just, if you look back here, it's just some function of omega n's. Okay, so let's go back down here. These are our steps. Determine omega n, then the DFT matrix. Omega n, of course, depends on n. We've defined the equation already. Omega n is equal to e to the negative 2 pi I over n. Well, n in this case, the number of elements is 4. There are 1, 2, 3, 4 components. So if n is 4, we could go ahead and write omega 4 is equal to e to the negative 2 pi I over 4, or that's equivalent to negative pi I over 2. Now, if you may recall Euler's equation. Euler's says that e to the ix, a complex exponential, is equal to the sum of cosine x and I times sine of x. So let's rewrite our this equation then in terms of using Euler's, and we'll see that omega n, or omega 4 in this case, is equal to cosine of negative pi over 2 plus I sine of negative pi over 2. Of course, we can calculate these values pretty simply. Cosine of negative pi over 2 is 0. And sine of negative pi over 2 is negative 1. So then we could rewrite omega n simply as 0 plus I times negative 1, or negative I. So omega 4 is equal to negative I. Great, so we have we've done that. We found omega n. Now we need to find our DFT matrix. Our DFT matrix will be 4 by 4. Remember, we have J here and K here. So J will start with 0 and go to 3. It's n minus 1. N is 4, n minus 1 is 3. And K will be the same, 0, 1, 2, 3. Of course, you'll remember that the top row and the first column are 1s. And every element inside, even these top rows and top columns, is simply this, omega n raised to the jk. So because in these cases, both j or k is 0, that makes this whole value go to 1. That's why all of these are 1s. But we can start filling in the values here. So here we have j1, k1, we would have negative I. Okay, so omega n, of course, that's going to be omega 4 to the jk. We've determined omega 4 is negative I. So it's negative I to the jk is what we're putting in there. So here we have negative I. Here we have negative I squared. Here we have negative I cubed, negative I squared, negative I to the 4th, negative I to the 6th, negative I cubed, negative I to the 6th, and negative I to the 9. Okay, now we can rewrite this, we can simplify it. You'll recall that since I is negative, or square root of negative 1, then of course negative I is negative square root of negative 1. So this can get tricky, but the answers here when we simplify will just be combinations of negative I, positive I, 1, and negative 1. So if you take, here we'll have 1, 1, 1, 1, and 1, 1, 1, 1. Here is negative I, so that's just simply negative I. Negative I squared gives us negative 1. Then we have negative I to the 3rd gives us I. Negative I squared, again, gives us negative 1. Negative I to the 4th gives us 1. Negative I to the 6th gives us negative 1. Negative I to the 3rd gives us I. Negative I to the 6th gives us negative 1. And negative I to the 9th gives us negative I. All right, so let's take this then and do our matrix multiplication. So again, to get F, we do this matrix multiplication where we have our DFT matrix, which we just calculated here. So we've done that. Now we just need to do the multiplication. We have 1, 1, 1, 1, 1, negative I, negative 1, I. 1, negative 1, 1, negative 1, and 1, I, negative 1, negative I. We're multiplying that by little f. Little f is given here. It's 1, 2, 3, 4. We just multiply here. 1, 2, 3, 4. Great. Now to do matrix multiplication. To do matrix multiplication, we take this, we multiply it by this, element by element. So we'll have 1 times 1 plus 2 times 1 plus 3 times 1 plus 4 times 1. So let me write that here. 1 times 1 plus 2 times 1 plus 3 times 1 plus 4 times 1. All right, now to get the second row, we take this vector and multiply it by this and add all the components. So one by one, we multiply. So 1 times 1 is 1, 2 times negative I is negative 2I, 3 negative 1, and then 4 and I. So let's write that here. We have 1 times 1, so that's 1 minus 2I minus 3 plus 4I. The next row will give us 1 minus 2 plus 3 minus 4. And then the final row will give us 1 plus 2I minus 3 minus 4I. Let me copy this and put it on the next page. Okay, we can simplify this. So we'll have a real component and an imaginary component. 1 plus 2 plus 3 plus 4 is 10. There's no imaginary component, so we can say plus 0I. Here we have 1 and minus 3, so that's minus 2. And then the imaginary component, we have negative 2 and positive 4, so that's positive 2I. The next row, we have negative 2 plus 0I, and then negative 2 minus 2I. All right, so notice this is complex. We said it would be because we're multiplying our matrix. We're multiplying our matrix by a complex DFT matrix. We're multiplying our vector, our signal, by a complex DFT matrix. Great. So this is our answer. This is the highest frequency component. This is the lowest frequency component. Right? This is F. How do we do this in MATLAB? Well, MATLAB doesn't do the DFT directly. MATLAB actually does the FFT instead. So FFT is a computationally efficient way. It's a faster way for a computer to do a DFT. And it does it with the FFT command. So if we have a variable, we'll call it F. Excuse me, this is our input signal. We have 1, 2, 3, 4. FFT of 1, 2, or excuse me, FFT of F gives us exactly what we just calculated. 10, negative 2 plus 2I, negative 2 plus 0, negative 2 minus 2I, right? So what we just did by hand here is what MATLAB did for us using the FFT. Okay. I often find that it's easier it's helpful sometimes to put this in a vertical position. So if we transpose F, the apostrophe just transposes, so it just changes the direction. So often it can be simpler, can appear better if we do the transposition like that. It's just easier to read that than it is to read that, is all. Okay. Let's look at some properties of the DFT. The first is called linearity. So if we have two vectors, F and G, that are the same length, and we have scalars, P and Q. So these are just a number. If we multiply our vectors by the number, that scalar, and add them together, we get little h, right? So this is the time domain, you can think of it. If we do the DFT of F and the DFT of G individually, multiply by the scalars in the frequency domain and add them together, we get the DFT of H. Okay, so what this is saying is you can do that multiplication and addition by a scalar, multiplication by a scalar, addition of vectors in the time domain or the frequency domain, and you get the same answer. Right, that's linearity. This is the same as the Fourier transforms. This should be familiar to you. Another property is called shifting. Here we're doing something interesting, and that is we are making every other element change signs. Okay, so if we start with x, we can make a new vector called x prime, you could say. If we take the discrete Fourier transform of x prime, so we're going to get capital X prime, that's the same as if we took the DFT of x, so that would be capital X, and swapped the left and right halves, or the top and bottom halves. So let me show you what I mean by that. If our x is, for example, -1, 3, 5, 20, 2, -3. Our x prime is taking our values and swapping when n is odd. So here n is 0, n is 1, n is 2, and so on. When n is odd, just multiply by -1. So -1, -3, and so this one changes. 5 stays the same, 20 flips, so we have -20. Here, 2 remains the same, and then -3 becomes +3 because the sign flips. And that's x prime. If we were to take the DFT of x, that will give us capital X, and the DFT here would give us x prime. You'll notice that the values in this are the same except the order. So let's look at this in MATLAB to demonstrate. So the values we had were, let's say, x equals -1, 3, 5, 20, 2, -3. And xp, we'll just type it manually. -1, -3, 5, -20, 2, 3. Now we'll take the FFT of x and show it here. Here are the values, and the FFT of xp, and show the values here. Okay, so notice 26, -24.5, 15.5. Okay, these values are actually the same as these. So the first 3 here became the last 3, and the last 3 here became the first 3. All right, so this only happens when there's an even number of elements in your array. This does not happen when there's an odd number of elements. Okay. Let's look at another property. Testing. Okay, you should be able to hear me now. My headphones died. Hopefully the audio is clear up until now. So now let's look at another property of the DFT. Here's the example we just did. We're going to look at convolution. Convolution. Now you've done convolution before. You've done it in signals and systems. Maybe you've done it for a continuously defined signal, or maybe you've done it also for a discrete signal. Generally, convolution, let me just draw it out. It looks like this. You have 2 signals. You could say here we have x. X could look something like this.
And here we have y. Perhaps also this rectangle function. When you take x, what you do with it, when you do the convolution, you take it and see, no, I can't do that. You actually flip it left to right. Okay, so you flip it left to right. So this point here now is here. Of course, for this function, it looks the same. And then you multiply it by your other one here, in a sense. So you're going to take it and you're going to drag this one over on top of it. Okay, so when it's here, you're gonna multiply them together and record the value. Then you're gonna move it a little bit further, multiply them together, add the value. Move it further, multiply together, multiply together, multiply together. Of course, when you multiply, when they're totally overlapped, that's when you're going to get your maximum value. Then you keep moving it, and the value is going to decrease, decrease, decrease. Because if you look, for example, here and here, there's a 0 and there's a 0. So all those values will just go down to 0. In the end, what you end up with, your output for these two will actually look like this. That's the convolution of x and y. Okay, so here was that peak point when they are totally overlapped. Great. So that's just like regular convolution. If we were to do it mathematically, say, let's imagine we have f equals 1 f equals 1, 2, 3, 4. Actually, let's make this x. And then let's say y is 5, 6, 7, 8. To do this convolution, we're going to take x and flip it. So we'll have 4, 3, 2, 1, and then y is 5, 6, 7, 8. Let me make this blue. Okay, so I'm going to drop this down here. Say we have 5, 6, 7, 8. What we're going to do is the same thing. We're going to take this and we're going to move it bit by bit and multiply. So where these are aligned, we're going to multiply and add together. Here, they're not aligned, so we're not doing it. Here they are. So the value we get here is 5. It's 1 times 5. We're going to move it. Okay, so here we have aligned 2 and 5, 1 and 6. So we're going to add 2 plus 5, that's 10, plus 1 times 6. So that's 10 plus 6, that's 16. That's our second value. Then we're going to take it, move it again. Here we have 3 and 5, that's 15, plus 2 and 6, that's 12, and 1 and 7. I'll just calculate here, that's 3 times 5 plus 2 times 6 plus 7. That's 34. Okay, so we could keep going with this. I think I have that. Actually, no, I don't have it here. We can do it in MATLAB though. MATLAB, if we define x as 1, 2, 3, 4, and y as 5, 6, 7, 8. Convolve these, convolve x and y. And we get the values 5, 16, 34. The next one is 60, then 61, 52, and 32. So I wrote them down here. All right, so that's kind of doing it visually. You take it here, you move it, keep moving, you keep moving, you keep moving. So that's why you see the last one is 4 times 8, that's 32. You move it again and they're not overlapping anymore, so it's done. Great, so that's kind of a way to do it visually. There's another way to do it. If you go back to your original, you have x 1, 2, 3, 4 and y 5, 6, 7, 8. You could calculate it like this. So you have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, first you can take 5 and multiply it by every element. Put it here. So you have 5 times 1 is 5. 5 times 2, 10. 5 times 3, 15. 5 times 4, 20. Then you can take 6, multiply it by every element. But instead of starting to write here, you write in the second spot. So 6 times 1 is 6. 6 times 2 is 12. 6 times 3 is 18. And 6 times 4 is 24. Then you can take 7. And again, put it in the third spot. So 7 times 1 is 7. Then we have 14, and then 21 and 28. And then the last one, 8, you have 8, 16, 24, 32. Then to get your final answer, all you do is add these together vertically. So here, 5, here, 16. Here, you can guess perhaps what it is, 34, then 60, then 61. Okay, so that's 2 different ways to do convolution. That's regular convolution, the kind of convolution that you've studied so far. Now, what we're going to talk about is actually called circular convolution, which is slightly different, very related, but slightly different. So we're going to suppose that x and y are vectors of the same length. The length is n. And we're going to define circular convolution using this kind of same symbol, z. We're going to define it as z. And here's the equation. So the kth value in z, by the way, z will be the same length of, it will have the length n. The kth value in it is defined like this. Okay, so I put the equation in the top right. Let's think about it. So here is, I'll go ahead and write this on my screen. So here we have 1, 2, 3, and 4, and then 5, 6, 7, and 8. And let me just write the equation. Zk is equal to the sum n equals 0 to n minus 1, xn, y, k minus n. Okay, let me show you the screen now that I have it written. Here it is. All right, so this is x, and this is y. This is n equals 0. And we're going to start defining our z. We're going to start at k equals 0. So z at k equals 0, let's just look at our equation. K is 0, so that means this value is 0. And we're going to start from n equals 0 and go to n minus 1. Okay, so to get the first value here, for k equals 0, it's going to be the sum of x n. So n at first is 0, so that's 1. That's 1 times y of k. Remember, k is 0 and n is 0, so y is 0. That's there. So 1 times 5. Plus, we're gonna move the value of n up to 1. So now n is 1. X1 is 2. So that's 2 times y. So that's a 0 and that's a 1. So 0 minus 1. Y minus 1. Uh-oh, how do we do that? Well, for circular convolution, what we're going to do actually is tile y. So we're going to have 5, 6, 7, 8, 5, 6, 7, 8, as far as we could go. Okay. And we're going to define this now as n equals 0. So this here would be n equals -1. So y -1 is 8. We can just kind of go this way, or you could think of it as tiling. So this is n equals 0, n1, n2, 3, or -1, -2, -3. So -1 is 8. So it's 2 times 8. Plus, it's going to be 3 times 7. So you can see what's happening. In X, we're moving this way, and Y, we're moving this way. So we did 1, 2, 3. The next one is going to be 4. And in Y, we did 5, 8, 7. The next one's going to be 6. And that's just for k equals 0. So we do that. We could define it z0. 1 times 5, that's 5 plus 16 plus 21 plus 24. What's that going to give us? What's in the slides? 66. Okay, that's just for the first element in K or in Z. So that's Z0. We would need to do that for all 4 elements of Z. Okay, so you would just increase your value K to K equals 1, and then K equals 2, and then K equals 3. And that's just going to change this here. All right, so you can do it mathematically like that. Another way to do it is to think of it visually. Visually. So again, here, what we've done is we've taken X, and here we have Y. For Y, just 1 second. All right, so we have our X here. What we're going to do with Y, if you remember how we did this visually before, is we flipped one of them. So here we're flipping our Y. So instead of going 5, 6, 7, 8, it goes 5, 6, 7, 8. And we're tiling it. So 5, 6, 7, 8, 5, 6, 7, 8. We could keep going if we wanted in both directions. It's tiled. To start off with, what you want to do is align the first elements, the n equals 0 elements. So that's 1 and 5. They're in red here, like they were in red on the previous slide. All right. Sorry. So here they are, the n equals 0 element, both in red. Both in red. We're aligning n equals 0, and we're going to do the math. So 1 times 5 is 5. Plus 2 times 8 is 16, plus 3 times 7 is 21, plus 4 times 6 is 24. We sum those together. That's 66. That's our first element. Now what we're going to do is slide Y over 1. And we're going to do the same. 6 plus 10 plus 24 plus 28, that's 68. Okay, you can see the math. This 5, 16, 21, 24, that's the same as we had here. 5, 16, 21, 24. It's the same. We're just doing it visually now. Okay, so we slide it over, we get 68, we slide it over again, multiply, add the elements, we get 66, slide it over again, multiply, add the elements, okay? We get 60 and we're done. The reason we're done is because if we slid over one more time, there would be a 5 here. We can tile continuously. The 5 would come back here and it would look just like it did the first time, and we'd get 66. And this would just repeat itself. 66, 68, 66, 60, 66, 68, 66, 60, and so on. It's a circular convolution, right? We just go in a circle. Okay. Let me show you one other way you can do this. So we talked about how to do it mathematically. We use the equation that's here. We talked about how to do it visually. That's what I just showed in the slides. Let's go back to how we did convolution here. Okay, if you remember, just the normal convolution, we ended up with an array that's much longer than 4. We need it to be 4 though. So to convert this to a circular convolution, from a regular convolution to a circular convolution, we're going to count 1, 2, 3, 4, and then draw a line. We're going to take these values, move them to align the first, second, and third. Okay, wherever it kind of overlaps, you just take it there. So you take what's left and you move it to align at the beginning. If there aren't enough to fill it, that's fine. And then you just add 5 plus 61, 66. 16 plus 52, that's 8 and 6. 34, 32, 66, and then 60. Okay, so you'll notice that this is exactly the same as what we just calculated with the visual method. Right? Exactly the same values. So multiple ways to do it. Depends on you, how you want to do it. But that's how a regular convolution is related to circular convolution. Let's talk about the convolution theorem. Suppose that x and y are vectors of equal length, then the DFT of their circular convolution, x convolved with y, is equal to the element by element product of the DFTs of x and y. I find it easier to think about this mathematically. So the convolution of x and y, you can get that by doing what we just did, right? What we just showed how to do. You can get it like that. Or you could take the DFT of x and the DFT of y, multiply them together, and then take the inverse DFT. And that would give you the exact same answer. All right, so let's think about, let's prove that in MATLAB. Let's show that that's true in MATLAB. Again, in MATLAB, we have x and y. These are the same, they've been the same through the whole class today. We could first do the circular convolution. In MATLAB, that function is CCONV, circular convolution. We'll do x and y. Again, I'm only putting the apostrophes because it shows up better, it appears better. And then we're gonna put the number of elements that we want. So in this case, it's 4. If we press enter here, we'll see our answers: 66, 68, 66, and 60. That's exactly what we calculated before. If we do circular convolution without adding the 4, we just get the normal convolution, the same as if we were to write CONV, x prime, y prime. All right. So again, clear the workspace. This is what we want. This is the circular convolution with 4 elements. Now, what we want to demonstrate is that the inverse DFT, which MATLAB calculates with the FFT, the inverse FFT of x multiplied element by element, so we need that dot to do element by element, of the FFT of y should give us the exact same results here. Let's see if that's true. It is. Okay, we calculated at the beginning of class the FFT of x. You might remember this. We could also do by hand the FFT of y. You'd get something like that. You multiply those together element by element. So that's 10 times 26 and -2. So we could just kind of show what this is here. All right, so that's 100 multiplied by this. If we take the inverse Fourier transform, inverse fast Fourier transform of that, then we get the answer. This is the same as the convolution, the circular convolution of x and y. Okay. We will end class there today. It's a lot to digest, perhaps. I recommend working through this in MATLAB and working through it by hand without watching the lecture, just to make sure that you understand it and are able to do it. This would be a great question to have on the final exam. All right, if you have any questions, feel free to email me, or you can book office hours also. And I will see you next week.